Good morning, all. Are you able to see anything in your screen?
Yes, sir.
Yes, sir.
Is it slow, or are you able to see it? Is it lagging or anything like that?
Now you were showing just a slide of a PPT, sir, like column PPT. Yesterday we thought it lost line, no, sir. Now it's moving, sir. Yes, sir. Clear, sir.
It moved. It's not lagging or anything.
No, sir.
Okay, because everything is really slow for me today. I don't know why. I should have restarted my system, but I didn't do it. That's why it took time for me. It took this much time for me to actually start recording and then share the screen. Okay, really bothersome. Okay, anyway, so this was the slide we saw yesterday. Basically, looking at. Sir, I'll call you in half an hour, sir. So this is the arrangement of reinforcements typically that we can use in a column. So this is where we had stopped yesterday. Now we'll move to the behavior of columns. Okay, so typically we are looking at this stress strain curve of concrete, okay, which we saw much earlier in this course. Okay, so we see that corresponding to pure compression, we take the failure strain as 0.002, and corresponding to compressive failure strain in bending, we take it to be 0.0035. Okay, so in a column we may have a mixture of this. Okay, in a column, as I told you, you can have either pure compression or you may have compression with bending. Okay, so both cases are possible in a column. So therefore, we will investigate such cases. Okay, so let us take both cases together. One is if you have pure axial compression, then this is how the stresses will be distributed across your cross section. Okay, so if this is the cross section of your column, if it is taking pure axial compression, then this is how the this thing will be distributed, your stresses. And you know, if it is going to be a beam or if it's going to be bending, then this is how the strains will be distributed. It will be distributed in the form of a triangle. I mean, this double triangle which we have already seen. And thereby, our strains in concrete, you know, it's going to be 0.035, and in the steel, it will be either epsilon y or epsilon st. I mean, whatever the stresses in steel might be there. Okay, so depending on the relative value of the compression and the relative value of the moment, you may have different shapes of stress distribution, which is basically a combination of a rectangle and this double triangle. So you can combine this in various ways and you'll be able to get different types of failures in columns. For example, so I have just shown two things. One is pure compression, pure bending. Okay, these two things are shown. Now, if let us say that I am fixing this bending. Okay, so this bending profile is being fixed, and I keep increasing my compressive strain. The compression, I keep increasing the compression in my column. So if I keep increasing the compression in my column, what happens to this rectangle? What happens to the rectangle if I keep increasing the compressive force in the column, axial compression in the column? This is the stress distribution for pure compression, and I keep increasing the compressive force. So what happens to this rectangular stress distribution? What happens to it?
It becomes large.
It becomes
Large.
it becomes taller. It becomes larger and larger. So the value of this compressive stresses become more and more. So what you should notice is compressive forces will add with compressive forces, and compressive forces will be subtracted by this tensile stresses, not forces, stresses. Okay, so as this rectangle becomes larger and larger, if I combine it with this picture, then what will happen is this side will keep getting larger and larger, and this will become getting smaller and smaller, because no, this is adding on to this. Okay, so when this happens, what will happen is, so no, this is becoming larger and larger. The compressive part, this part of the double triangle is becoming larger and larger because of this, because this is becoming larger, and this is becoming smaller and smaller. So what will happen is, what was the neutral axis, no, at this particular location, it keeps moving to this side. Okay, because this triangle is becoming, I have not shown it properly. I should have drawn this a little bit bigger so that it would have been a bit easier for you to understand. But anyway, I have not shown it. So so what will basically happen is, this becomes more. Of course, your strain in concrete cannot increase. Okay, it is 0.0035. The strain cannot increase beyond 0.0035. So in effect, basically you're looking at only this axial strain getting subtracted with this tensile strain, and this triangle becoming smaller and smaller as the compression keeps increasing. So the vertex of this triangle keeps moving to this side. Okay, the vertex of this triangle keeps moving to this side because this triangle is becoming smaller, and therefore, as you keep increasing your compressive force, the neutral axis or the balance point, whatever you want to call it, it keeps shifting towards this side. At one fine stage, what will happen is, you may have so much compression, and the compression may be so much greater than the bending moment that when you look at the strain distribution, you may have a strain distribution like this, where you do not have anything beyond, it reduces to a single triangle, meaning that this is a case of no tension. There is no tensile stresses at all in the cross section of this column. Okay, so this is known as a no tension case, and I say in that particular case, my neutral axis is at the depth of the column or at the edge of the column. So this is one case. Further, what I can do is, I can still keep increasing the compression, and I can increase it so much that compared to the axial compression, the bending moment is almost negligible. Okay, or in other words, I come to a case of pure axial compression. So at this case, I say my neutral axis is at D. If I have only pure compression, then it is not it's no longer a triangle. It's just a rectangle. Okay, and I cannot identify any point as neutral axis at all. Okay, so if I want to identify neutral axis, I need a point where compression changes to tension. In pure compression, I do not have such a point, and therefore the pure compression is like a case where my neutral axis is at infinity. Okay, meaning that the neutral axis is not at all present in this picture. Okay, because it's a rectangle, not a triangle. So this is very simple. It's just a combination of shapes. It's a combination of this rectangle with this double triangle, and as this rectangle keeps becoming bigger and bigger, this triangle keeps becoming smaller and smaller. Okay, and that is what reduces to this case at one fine point, and if it keeps increasing much larger, it becomes this. Okay, basically you have just the rectangle. So when axial loads are higher, tensile strengths in the reinforcement on the tension side of the neutral axis keep reducing, while the strain on the reinforcement side keeps increasing till the point where you have 0.0035. So what we see is, therefore, the neutral axis keeps shifting based on the values of moment and axial compression. M and P is axial compression and bending moment. So as the relative values of moment and axial compression keep changing, the neutral axis keeps moving. Okay. So in other words, that can be shown typically in can be shown like this typically. So there is a point where you have something known as a balanced failure, which is very similar to your what you saw in beams. No, it's very similar to that. This balanced failure point given by this CB, it is the situation where the moment and the compression are of such values that you have 0.0035 or the failure strain in concrete, and you also have simultaneously the failure strain in steel. Okay, yield strain in steel. So that particular combination of bending moment and axial compression, so we call that combination as corresponding to a balanced failure type. Now what happens is, if if my bending moment is lower than this, then I will have compression failures. Then because my axial compression is more. So for any value of bending moments lower than that corresponding to this balanced failure, I will have either this type of, I will have my strain distributions like this. Okay, where the neutral axis is towards the it's the neutral axis towards the tension side is much lesser. Okay, so neutral axis is at this point. For balanced it is over here. Then I keep increasing the compression, the neutral axis may move to this point. I can increase it further, it may move to this point, and then if I increase it further, it may even move to this edge. Okay, and conversely, if I have bending moment values greater than the bending moment value which occurs at balanced failure, then I will have my strain distribution moving like this. Okay, so meaning that the neutral axis keeps moving more towards the compression side. Okay, so it's basically just a representation of what I showed in the previous picture, except that there I showed tension side on the right and compression was on the left. Here it is reversed. That's it. But otherwise it's the same. So for all these strain profiles, okay, till the balance video. So this, and this, the compression steel will not yield. Okay, of course it is only compression. When the compression steel does not yield because it is a tension failure. Okay, so the location of the neutral axis is lesser than the location of CB, and the strain in steel equals Fy. Okay, and these two ones are typical compression failures. Okay, so this is what is basically just shown over here. You can just a re-representation of what was shown before. So one difficult thing is now, how do I know how do I find my neutral axis? For a beam, it is very simple. For a beam, there is no compression in a beam. It is only bending moment. So therefore, you have your famous formula: XU equals what for a beam? How do you find it? For a beam, under reinforced beam, how do you find XU? What is the formula?
0.878.
Yeah. So obviously you have that simple formula to use. That can be used because you do not have any compression. Here you have two things: compression is there, and then bending moment is there. So depending on the relative values of both, your neutral axis will be present somewhere which you do not know where it will be present. So therefore, there are some clues given in SP16 which you can use. Okay, they basically give one parameter called as K, known as XU by D. Okay, and for such cases, they just tell you what is the area of the stress block, what is the distance of the centroid from the highly compressed edge. Okay, so basically to locate this point, they give you some tables that you can use. Just I want to show you this. You will not be using any of this. You will not be doing such problems which involve finding the interaction between moment and bending. You will not be doing it, but this is there in SP16. I just wanted to show it. So as I told you before, depending on the relative value of your axial load and bending moment, you may have different locations of neutral axis. Okay. In addition, you have a few cases. One case is, assume it is a column which does not have any bending moment. Okay. So in such a case, you consider the column as a typical column, and you will be able to calculate or find its axial compression capacity. The design axial compression, you will be able to calculate. I have not told you what the formulas are yet, but anyway, there is a formula, and you will be able to find out what the design axial compression for a column is if it does not have any bending moment, like a pure or an ideal column. The other end of the spectrum is you have a beam, you have a normal beam, no compression, nothing, only bending moment. Okay, so that also you have studied in your unit number 1, where you have beams, you know how to design you know how to find the design moment at the moment of resistance. Okay, you know how to find the moment of resistance of any given beam. So that is this one. Okay, where you have only pure bending. The other one which I told for a column with only compression, it's only this one, axial load only. Now, how about if there is a column which has both of it? It has compression, it also has bending moment. How do you know when will it fail? Okay, so if it is only one thing, only axial load, you can calculate easily how much will be the capacity. If it is only a perfect beam, you know how to calculate its capacity or its moment of resistance. If both moment and compression are also there, both of them are there, then both of them have a part to play in the failure of the column. So therefore, we have this kind of a diagram which gives you an envelope saying as long as the moment and the axial load are within this envelope, you do not have any failure. Okay, if the values of load or moment fall outside this picture, then there's a likely failure of your beam, of your column. Okay, so there are two regions to this. One is it starts from here, reaches a maximum, and then slightly reduces and has a part over here. So this maximum point corresponds to a balanced failure. So, for example, for this particular column with this arrangement, this column will fail when the moment reaches this much value and the load reaches this much value. It will have a balanced failure in this particular column. Okay. However, within this region over here, as long as I have combinations of load and moment along this particular line, then this corresponds to a compression failure where your column will fail like a column through compression. If the combination of axial load and bending moments are within this region over here in this line, then your column will fail like how a beam fails. Okay, it will fail through bending. So what you can observe is, as long as I have more axial load and lesser moment, okay, so more axial load and lesser moment, I have a compression failure. As long as I have lower values of axial load and higher values of bending moment, I will have a bending type of failure, and you have a balanced failure at one particular point. Okay, so this type of a diagram, it is known as an interaction diagram. It's known as interaction diagram because it is stated that moment and axial compression, they interact to cause the failure. Okay, so this is for one particular column. Like this, your SP16 will have several interaction diagrams for several cases, several column cases. Okay, so when I show SP16, I'll show it. So basically, this is taken from somewhere else. This is almost straight lines. So it's composed of a straight line here and another straight line. So these look like straight lines, but in your SP16, it's more accurate. They have curved lines. Okay, so it is more accurate. So these are some aspects with regard to the failure of columns. So what happens when you have columns which are having bending? What happens when you're having columns which do not have bending? Okay, so these are some differences that you should understand. So coming to the provisions in our code book, we have some provisions. We'll start with the simplest case, which is a column without any bending moment. Okay, no bending moment. This is a column with pure axial compression. Now recollect yesterday that I told you there's a provision in IS 456 which says that whenever you have a column, you should consider some eccentricity. Okay, because in real there will be some eccentricity if you do not, and you want to be safe, so that you check what the eccentricity should be taken for that particular column. So there's a formula L by 500 plus D by 30. Okay, so you calculate that and see whether it is greater than 20 mm. If it is greater than 20 mm, you adopt that value. Otherwise, you adopt 20 mm as the eccentricity. So you have an eccentricity. Now what you will do is you will check whether that eccentricity which you calculated is lesser than 0.05 times the lateral dimension of the column. For example, if I have calculated my eccentricity to be 20 mm, okay, then my lateral dimension should be at least 20 by 0.5. I suppose it's no, 20 by about 400. It should be at least 400 mm. The lateral dimension should be okay. So like that, you need to check whether the eccentricity which you calculated does not exceed 0.05 times the lateral dimension, and if that condition is satisfied, you can just use this formula to find what your you can just use this to find what your capacity of the column is under pure axial compression. So you can use this, or you might as well more accurate formula is to use this particular one. Okay, so both things are there. Okay, so you can use this. These are somewhat straightforward expressions that you can use to calculate the bending capacity of a column, having only compression, and also it has low eccentricity, meaning that the eccentricity does not exceed 0.05 times the lateral dimension. So as long as those conditions are satisfied, you can just go ahead and use these two formulae. Okay. Now in the other case where either you have bending moment separately, or if your eccentricity exceeds this value, then you will have to actually consider the interaction between moment and bending and axial compression as probably shown by these figures. So there are two ways of doing it. One way of doing it is to actually do this. So you have, so basically all these equations they represent they actually represent these interaction diagrams. Okay, so you have something for the axial load, you have something for the moment as well. Okay, and this involves a lot of things, like for example, there are some constants. Okay, then there are some there will be some more things. Okay, YA. Okay, meaning the centroidal distance. YA is the centroidal distance. Then there's a constant. So all these things are there which need to be calculated. Okay, which is a painful process, to be very honest with you. So it may require iterations in a computer to do it. Okay, so it's written over here. The design of member subject to combined axial load and uniaxial bending will, in uniaxial bending means bending along one axis. And there's a even worse case, biaxial bending, means there's a moment this way, in addition to axial compression. Okay, so even for uniaxial bending and axial load, it involves lengthy calculations by trial and error. So nobody wants to do this. So only for this reason, people use interaction diagrams. Okay, these have been prepared and published in SP16. You can use them when you have a problem of uniaxial bending and axial compression. Okay, so we'll have a look at those things anyway later. So we saw some reinforcement arrangements yesterday. So let's look at some requirements which are stated in IS 456 with regard to the reinforcement. Okay, so one thing is I told you yesterday there is a good advantage of having spiral reinforcement rather than having separate individual hoops. Okay, so that is stated over here. If you have a compression member with helical reinforcement, this helical means this spiral, like your DNA. If that is the case, then you can take the strength which you calculate as 1.05 times the strength of a similar member with separate ties. So what is this 1.05 times the strength of the member? Basically, you can take 1.05 times whatever you calculate over here. So if you get 100 kilonewton as 100, so you get 1000 kilonewton as the capacity from this formula, then you can take it as 1050. Okay, if you have a helical reinforcement. So you cannot always do it. You should make sure that this helix satisfies this condition. Okay, so ratio of the volume of a helical reinforcement to the volume of the core shall not be less than 0.36 Ag by AC minus 1 into FCK by Fy. Okay, so you need, so this is a helix. If you know its diameter and you know its pitch, you can calculate the volume of the helical reinforcement. Okay, so when you do a problem, you know how to do it. So the pitch of the helix and the diameter of the bar need to be known to calculate the volume of the helical reinforcement. You have that, then compare it with AG is the gross area of the column, AC is the core area of the column within the helix. Okay, so what is the concrete contained within the helix? That is AC. FCK you know, FY you know. So you just check whether it is at least this much. So if it is at least this much, then you can do this modification. Okay, so and then all this minimum and maximum criterion. So the maximum column reinforcement is 4% of the gross area. Okay, and in some cases, if it's unavoidable, you can maximum take it up to 6%. The minimum reinforcement that you should give in a column is 0.8%. Okay, all these are with respect to gross area, they are not with respect to the effective area. Okay, like what was done for beams. Okay. As far as possible, provide at least 12 mm bars as the longitudinal reinforcement. Don't give 10 or 8, things like that and all. And this already told you, if it's a rectangular column, you need to give at least 4 bars in the corners. And if it's a column, if it's a circular column, you should give at least 6. And the spacing between each reinforcement should not be more than 300 mm. Okay, so if you have a very large rectangle of say the side is 500 mm or 600 mm. Okay, so when you give reinforcement at the corners, the spacing will be more than 300 mm. So in such case, what you should do is you should give another one in the middle. You should give another reinforcement in the middle so that spacing is not exceeded by 300 mm. So what you can do is probably, so instead of, so what you will do is probably if it's 600 mm diameter, 600 mm length side, instead of giving say 2 bars of 16 mm diameter, you may give 3 bars of 12 mm diameter, so that the spacing is also taken care. And no point giving 316 because it will be too heavy. So you can make it 3 times of 12. So these are all small adjustments that you can make. Then coming to the ties, okay. So these ties, basically I told you the function of these things. They provide buckling restraint to the bars, they confine the concrete, and they also provide ductility for the column. So these are the advantages of, or the benefits of giving a tie. So the pitch of the ties has to have these conditions. So it should be either, it should be lesser than the least dimension of the column, or 16 times the column dia, the longitudinal diameter. So 16, so if it's 12 mm diameter, then 192 mm. Hello? ஆமா அப்போ ஆமா ஜனவரி ஆமா அப்போ சரி கொடுக்குறேங்க. வரணுமாங்க? எங்க சொல்லுங்க. அந்த இதுதான் அந்த ஃபார்ம் ஒன்றுக்குமே தான் கொடுத்தேன். சரி அடிக்கிறேங்க. சரி அடிக்கிறேன். யாரோட சொல்றாங்க? கஸ்தூரி மேடமா? சரி ஓகே. ஓகே சரி கஸ்தூரி மேம் தானே? சொல்லுங்க. கஸ்தூரி மேம் தானே பார்க்குறேன். சரி சரிங்க மேடம். சரி மேடம் கிளாஸ் எடுக்கேன். மேடம் வந்து பார்க்க சொல்லிட்டீங்களா? வந்து பார்க்குறேன் மேடம். மேடம் வந்து பார்க்குறேன். மேடம் வந்து பார்க்குறேங்க. மேடம் பார்க்குறேன் நான். ஓகேங்க. இது பண்ண போறாங்க. சரி. Okay, so there I was. So we are looking at the pitch of the ties, and we say it should be lesser than the least of these. Okay, lesser than the least of these. So those are the smallest dimension of the column, 16 times the column reinforcement, and 300 mm. So among this, whichever is the least, the pitch should not exceed that. The tie diameter also has a restriction. So it should be either the 1/4, it should be 1/4 of the column reinforcement diameter. So for example, if it's a 20 mm, let me say 25 mm bar. Okay, 1/4 of that is about 6. Okay, or 16 mm. Okay, so whichever of this is lesser. Okay, so it should be greater than the least of this. Okay. Then helical ties sort of pitch one. If you look at the pitch of the helical ties, it should be 75 mm or column diameter by 6, and shall not be less than 25 mm or 3 times the bar diameter. Okay, so these all you can just read, you will understand what they basically mean. So it's a given separate condition for normal ties and helical ties, because for helical ties we need a much closer spacing in order to achieve the confinement in concrete. Okay, without giving this proper confinement, you cannot take this 1.05. Okay, that's why the spacing and other requirements are a little bit more. It's a little bit more stringent as compared to normal ties. So when the length of the columns is quite long, then different longitudinal reinforcements can be spliced as shown above. So what this is saying is, say if you have a very tall column which is say 10 meters or more in height. Okay, so it is difficult to give a single reinforcement of 10 meters height when you actually make the reinforcement arrangement. Okay, so in such a case, if you are allowed to actually splice different reinforcements together. So these are some options how you can actually splice it. So bottom there's a column, top there's another column. So the top column the reinforcement is here, bottom column reinforcement is here. Okay, so you can just take it, and then so you need to lap the reinforcement coming from here and the reinforcement coming from here. You should lap it in a particular zone like this, and this lap length also has some requirements. Okay, so you would have heard of development length. You would have heard or not, I don't know. Okay, anyway, so based on the development length, you can actually calculate how much this should be, and you should give at least that much distance. So this is one option. Or you can do this, or you can bring this inside. So there are several options are there for you to actually lap them. These kind of lapping arrangements are also, I think, would be shown to you in SP34. So if you open SP34, I think they should have given different ways of actually lapping the column reinforcements. Okay, so this is about biaxial bending. It's so it will occur quite a lot actually. It will occur a lot in normal framed buildings. Okay, especially the exterior columns of buildings. Okay, when you have an exterior column of a building, you will have a column. There will be a beam on this side. There will be a beam on this side. So the column itself will have some axial compression. Then this side there will be a moment. This side there will be a moment. Okay, so in corner columns of a frame building, you will have quite a bit of biaxial bending, meaning bending along x direction, bending along y direction, and axial compression. Okay, but many times this is avoided because many of the edge columns. Okay, one of the spans will be large, other span may be small. Okay, so one of the directions there will be large moment, other direction may be a relatively small moment only. Okay, so in many times what people tend to do is, even if they have biaxial bending, they will calculate a uniaxial bending load, uniaxial bending capacity, and then they will make the column much stronger than what they require, so that just somehow it also takes care of the other direction bending. Okay, it's not the accurate thing to do, but that's what many times it's done in practice. Okay, and other thing is, when you have corner columns with moments in two directions, usually it will have very less axial load. Okay, if there is a corner column and it has good amount of moment in two directions, then you'll most of the time find that the axial load is much lesser as compared to the moments. So in such a case, you can just design it as a beam and check it for both the axes. Okay, so this is one thing. So the biaxial bending causes compression tension pairs about both the axes. Hence the neutral axis becomes inclined. Okay, So basically, whatever you saw before, okay. So basically, you have you have your strain triangles like this. Okay, this edge is vertical, this edge is vertical. Okay, so when you have biaxial bending, it will not be like that. Okay, so you will have an orientation of stresses which is not either aligned with this edge, it's not aligned with this edge either. So the stress distribution will be the actual final stress distribution due to both mz and my. It will be a resultant. When I say resultant, obviously you know that when you have x and y, two different forces, the resultant will be inclined. The same thing. So you have moment about x, moment about z. The stresses caused by or the strains caused by those mz and my movements will again have a resultant, and that resultant will be inclined. Okay. So therefore the neutral axis also becomes inclined. And this inclination and this resultant will depend on the relative values of mz and my. So even uniaxial bending, it's a pain to actually solve manually. Biaxial bending, we can forget it. Okay. So due to the effects of the three components, the analysis is even more complex, and you need again a much severe trial and error approach. So even for biaxial bending, you have in your SP16 an interaction diagram to help you, but this interaction diagram is a little different in the way that for uniaxial bending, you have one axis is compression, other axis is moment. For biaxial bending, we will have a different type of interaction diagram where one axis is one of the moments, the other axis is the other moment. Okay, so this is how it changes, and your so which curve to take depends on what the value of your axial load is. So if the axial load divided by the axial capacity is 0.9, you can take this. If it's 0.8, you can take this, etc. Okay, so like this we have several curves. So when we do it, we'll see it. So in the most better way to actually draw the interaction diagram is a 3D surface. Okay, where one axis is P, other axis is one of the moments, other axis is the other moment. Okay, so you see that each of these curves is like your same thing. Okay, what we saw for your uniaxial moment compression, no? So each of these curves, each of these lines represent one such curve. Okay, so as long as you're here, this means both my and mz are 0. So if I come somewhere over somewhere to this point, okay, then I can have about this much value of my and mz, as shown by this curve. So you have curves like this, you have curves like this. Okay, so it becomes a 3D plot. So the interaction diagrams can also be made for biaxial bending, except now it's a 3D plot. For a constant axial load, for any constant axial load that you take, if I take this value of P, then I have this curve. And this curve is what is shown over here. Okay. So in the curve, you can actually use, in the code book, you are shown this particular interaction. This is known as an interaction equation, where basically Okay, I think I lost track of the sound because of this disturbance in the middle. I had to come out of it. Anyway, so I was looking at biaxial bending. I'll continue it in the next class. Something what I want to know is tomorrow, class rep, can you ask whether Gandhipati madam is taking for that section or should I take my class? Okay, just ask her and can you just tell me later?
Okay, sir.
Okay, just ask her whether she's taking the class tomorrow. If she's taking the class, then my class will not be there. We'll meet only again on Tuesday. Otherwise, I'll take. Okay, just ask and tell me tomorrow.
So what about our class, sir, like B class?
No, it's a common class now, so therefore I have to take together only. You will be free in that case.
Okay, sir. Thank you, sir.
Okay. Okay, fine. Then we'll meet later then. We'll meet either tomorrow or Tuesday. Let's see.